So let's do a little review on chapter 8 using the using version 1. There's a second version in there, but as usual, there's a lot of redundancy. Not necessarily the repetition, but same types of problems. So we can get everything we need out of this one. All right. So how much time do I have? Hour and 3/4 maybe? Hour and 40 minutes. Hour and 15 minutes. That's worse. We'll see how fast I can move. We'll start off slow. Basic stuff. I mean, this is not even chemistry. This is physics. Force between two bodies having identical electric charges, that force is always repulsive. Whether they're positive or both negative, doesn't matter. Number 1. Number 2, I don't even have to write that one up there. Atoms having equal or nearly equal electronegativities are expected to form what kinds of bonds? If they're both the same, I think I'll go right up here. If they're both the same or very close to the same in the electronegativities, then first of all, you should get a covalent bond. Right? Because nobody's going to win. Nobody's going to take electrons and leave the other one without. But also, if they're nearly equal, you're going to get a nonpolar covalent. Okay? So that's C, nonpolar covalent. Let's see. And in the beginning, I'm doing almost every one. We'll start skipping later. For these elements, cesium, fluorine, and chlorine. Cesium, fluorine, and chlorine. We want to order those according to increasing electronegativities. We need, which one is increasing? Oh, excuse me. Increasing. Which one is the most electronegative? Fluorine, right? On the Pauling scale, fluorine is 4.0. Nothing bigger than that. So this is, fluorine is the biggest. And what's the least? Right down here in the corner, cesium. Cesium and francium are exactly the same. So cesium is good enough. So cesium is the least electronegative. I think it's about 0.7. And then that just leaves chlorine for the middle. So which one is that? Fluorine, B. B works for number 3. But number 4. Let's see. The electron pair in CF bond could be considered. We're just looking at the bond. Doesn't have to be a whole molecule. Just these two atoms bonded together. The electron pair, and that's what this line represents. It's a pair of electrons. Could be considered what? Closer to carbon? Or is it closer to fluorine? It's closer to fluorine. Fluorine is the most electronegative. So we're going to have a dipole moment in that direction. So that means A is out, C is out, centrally located, E is out. Bond is not ionic. The difference in electronegativities is not enough to make an ionic bond. And one clue is they're both nonmetals. You don't get ionic bonds with 2 nonmetals. You gotta have a metal and a nonmetal, at least. So what's left? Closer to fluorine, B is the only one that has closer to fluorine. Because fluorine has a higher electronegativity than carbon. That's true. B is the only possibility. Let's see. Well, five. Try to phase that. It's going to get chopped off. Let's see what happens. That's good. Okay. 5. Which of the following molecules has no dipole moment? Okay. So here are our choices. Carbon dioxide, ammonia, water, and D and E's all or none. So this says that all have no dipole moment, or none have no dipole. That sounds like the same answer to me. So let's look at it. So in order to find out whether they have a dipole moment, we need to know what? We need to know, are the bonds polar? And what's the geometry? So we need to draw the Lewis dot structure for these. Valence electrons. Carbon has 4. Oxygen has 6. So that would be 16 electrons, right? So carbon dioxide, put carbon in the middle, oxygen's on either side. So that's 2, 4 equals 12 electrons that we have to position. Work from the outside in. So that's 6 and 6 is 12. They're all used up. Okay. Now you try to make an octet, if at all possible. So how do we make an octet out of this? Carbon has no more electrons. So we have to borrow from oxygen in such a way that we retain the octet for oxygen because it already has an octet, 2, 4, 6, 7. And gives carbon an octet also. So the simplest way is to make a double bond right there. That means 2, 4, 6, 8, 2, 4, 6. Oh, carbon needs another. So which would be the best? Make another triple bond on this side, or make another double bond on this side. Get rid of those two, these, that. Now the other one would be a valid Lewis dot structure, but how do we break the tie? You remember that? We've got another attendee, Brandy. Went to there so long. Gotcha. If we drew this one, how do we break the tie? It's called formal charge. What's the formal charge of carbon? Well, it comes in with 4 valence electrons. Now it has 1, 2, 3, 4. That's 0. Oxygen comes in with 6 electrons, valence electrons. It has 1, 2, 3, 4, 5, 6. Both of them are 0. So they're all 0, formal charge. If we do this one, then carbon is still 0, 1, 2, 3, 4. But this oxygen has 1, 2, 3, 4, 5. 4 minus 5 equals -1. That makes this one +1. So the best structure, Lewis dot structure for this one is the one where carbon is double bond on one side and double bond on the other. That gives the lowest possible spread of formal charges. All right, now after saying all that, what's the structure? When you have 2 groups around the central atom, there's only one possibility. It has to be linear. So as written, it may have, it does have, a dipole moment this way and that way. And they're exactly opposite one another. Bond diagonal, 180 degrees, which means that this one is nonpolar. This one has no dipole moment. Now, since we have these choices, let's go ahead and do the rest of them, because we might need those structures later. Okay, so if we draw ammonia, nitrogen has 5 valence, hydrogen contributes 3, 1 each. So 5 and 3 is 8. Right, there's 1 in the back. Let's see. Hydrogen back here, hydrogen out here, hydrogen out here, and well, actually, I'm getting ahead of myself. We're going to do it kosher way. Nitrogen, like that, like that, like that, like that. Okay. 2, 4, 6, and we have 8 to go around. So 2 more. None of the hydrogens can take any more electrons. So we have to put the extra pair on the nitrogen. Okay. So the electronic structure with 1, 2, 3, 4 groups is tetrahedron. But if we cover this one up, we draw the tetrahedron. Let's do that. That. And then we put the nitrogen in the center. And we have a hydrogen back here, a hydrogen here, and a hydrogen here, and the lone pair up there. So there's your electronic tetrahedron. But if we cover up that lone pair, what's the molecular structure? The molecular structure is a trigonal-based pyramid. So that's why I started to draw it like this. Here's our trigonal base right here. So the dipole moments are this way toward nitrogen. Right? Plus it has this lone pair, so the preponderance of negative charge is this way. That gives it a dipole moment. Right? So this one has no dipole. This one has a dipole. How about water? We've done water before. Water looks like this. Okay. Electronic structure is tetrahedron. Cover these up, now it's a bent molecule with dipoles this way, plus these extra long pairs. So it has a dipole in that direction. Right. So water is out. The answer to this one's A. That's the only one that has no dipole moment. All right. So let's see. And I'm still taking them in sequence here. Because they're different ideas. Each one is a new idea. When we start getting repetition, then they'll skip. Which of the following has the smallest radius? Okay. This one can be tricky. We talked about trends in the periodic table. Atomic radius. But that was for neutral atoms. Okay. Which says what? Lower left to upper right. Now, if you go across a period, why does the atom shrink going to the right? More protons draws those electrons in. Why does it get bigger as you go down? Because you're adding electrons to the energy levels. It just balloons, no matter what the number of protons is. And those inner protons are shielded by the core electrons. So the outer electrons are not drawn as tight. So, with that in mind, what do we have to go on? Well, let's see. We have the same ions. It looks like the same ions in each group. So we just need to deal with that. So let's see. We have gallium, calcium, potassium, chloride. Calcium, potassium, chloride, and sulfur ions. Okay. Here's the way we solve this problem. Notice, these are all the preferred ions for these elements when they join in an ionic compound, which means that they probably look like a noble gas. So let's see if they all look like the same noble gas, that means they're isoelectronic. They have the same electronic structure. So let's see. Calcium and potassium. Yeah. 2 plus calcium looks like argon. 1 plus potassium looks like argon. 1 minus chlorine looks like argon. 2 minus sulfur looks like argon. These are all isoelectronic with argon. Okay. Now, gallium doesn't fit there because gallium is way down here. Let's see, way over here. So a 3 plus gallium. Well, it's trying to look like argon, except that it's got all these d electrons in it. The 4s orbitals are good, but argon doesn't have any 3d's. So we have to treat this one separately in just a minute. Let's put these in order. If these are all the same electronic structure, they don't have the same number of protons. So which ones has the most number of protons? It would be calcium, right? Same number of electrons, the most protons, except for gallium. Let's write those in. This is 20, 19, 17, 16 protons, and gallium has 31 protons. Okay. Okay. So the one with the least number of protons should be the biggest, has the least attractive force for all those electrons. That means sulfur will be the least, and it looks like they're from in decreasing order. So sulfur would be way over here on the right. The next biggest one would be chlorine, or chloride. The next biggest one would be potassium. Next is calcium. And then because this has got so many more protons, right? It's got 11 more protons than calcium. And that what I'm thinking is those extra protons are sufficient to draw those d electrons in, because the d's are in the third orbit, the third principal quantum. So they're really not sticking out there that far. But with that many extra protons, I think gallium is probably the smallest. And that's my reasoning, okay, if that makes any sense. It would have been easy if we hadn't thrown gallium in here. That's the fly in the ointment. Any questions? We're good so far? About 7, about 8. In the reaction between magnesium and sulfur. So we got magnesium and sulfur. What are they going to do? Well, magnesium's metal, sulfur's a non-metal. The trend, and if they're far enough apart, which they are, they're in the same period. Sulfur is a non-metal, magnesium is a metal. More than likely, we're going to transfer electrons here. Back 2 of them. That makes magnesium 2 plus and sulfur 2 minus. And that's where you get your ionic bond. So the magnesium atoms become cations. They become positive ions. Yeah.
I wanted to ask, question 7 I just did. When we're on the board, there's no answer. There wasn't, you said sulfur was the smallest, they said, gallium was, oh, sorry, so gallium was the smallest, they said sulfur was the next smallest.
Oh,
Chlorine,
did I put them in the wrong order?
uh,
I think I did.
okay,
Yeah, so it should have been sulfur first, then chloride, then potassium, then calcium. Because calcium has the most number of protons. So we're shrinking as we go from left to right. Yeah, that was my mistake.
okay.
It should have been this order. Yeah, the most number of protons would be the smaller one. So at least for these, it's simple. They're all isoelectronic. We're increasing protons to the right. So we're shrinking the size. And then we sort of had to rationalize this one. The only other option for this one is to put it over here. And that you'd have to argue that the three B's are sticking way out there when they're really not, because they're at energy level 3. So they're closer to the nucleus. And there's sufficient, 31 protons? Yeah. There's sufficient positive charge to draw those D's way down. Yep. I think everybody watching in television land get that? My mistake?
Yeah, I got it.
I put things in the wrong order.
Yes.
I was talking about it and writing it wrong. Okay. That was 8. Let's see what we're gonna do. Yeah, we're gonna do 9. Scroll it up. Okay. Choose the molecule with the strongest bond. This one is logical up to a point, and then we have to switch logic. With the strongest bond depends on 2 things. What's the bond distance? The shorter the bond distance, the stronger the bond. So if the nuclei can't get close together and you can't get sufficient overlap of orbitals, then you have a weaker bond. So these diatomic halogens are given in order that they are in the periodic table. So we're going down: fluorine, chlorine, bromine, iodine. So if we put them like this, let's see. That we would expect the diiodine molecule to be the weakest, because it's the biggest atom. Furthest apart, less overlap of orbitals. The bond distance is bigger. So this is the weakest one. And then as they get closer, the bond strength goes up. And we would expect that with fluoride, difluorine, this would be a stronger bond. So if we're going strength here. The problem is, once you get this close, once you get the nuclei that close to one another, they've got the positive charge here, and we've got the electrons here. You start to, the molecule starts to feel more repulsive force, particularly from the nucleus. And that counteracts the covalent overlap of orbitals that we would expect to bring the molecule together in a tighter bond. So it peaks at chloride, dichlorine, and then it drops off at difluorine for that repulsive effect. So the bond distance and consider the bond distance and then the possible repulsion of like charges. In that case, this one, B, is the strongest bond of the bunch. Now, that's a fact. we can measure how much energy it takes to break each one of these bonds. So what I've given you is the explanation. Like I said, nature just does what it does, and this is the explanation for it. So this is reality, and that's what I think happens. It's not like I make something up and then nature better fall in line or else. Okay, let's see, I'm gonna do, 10. The reason I didn't stop on 10 is because it's saying the same thing a different way. 9 says the strongest bond, and 10 says the greatest bond energy. It's just another way of saying the same thing. So 10's got the same answer. Now if we go down to, let's do it like this. Number 11, is that on my list? Yep, number 11. We're using these Roman numeral 1, 2, 3, 4, and 5 to answer the question. Which of the molecules obeys the octet rule? So in this case, you need to draw the Lewis dot structure and just see which one can obey the octet rule. Boron trihydride. We did this one in the lecture. That one's like this, right? 3 electrons here, 3 there, 6. So we only got 6 to go on. This is trigonal planar. And any dipole here is canceled out because they're equally spaced around an isosceles triangle. So this one's non-polar. Is that what we're looking for? Which of the following obeys the octet rule? No, it's not polarity we're talking about. This one is less than octet. That was less than octet. 2 is NO2, so we have to go ahead and draw this one. That's 5 here, 12 there because 6 for each oxygen, 17 total. So we got 17 minus 4 is 13 electrons. 6, 12. So now we got 1 left over. Has to go here. Okay. That's only got 2, 4, 5. We could make 7. Right? All we have to do is take one from here and do that. But nitrogen does not have, nitrogen and oxygen, neither one of them have d orbitals available because they're only second period. Right? Second period doesn't have any d orbitals. So that's as far as we can go. We can only go up to 7. We can't go over 9 because there's no place to put it. So this one does not. This one's less than octet also. Or we could have drawn the double bond on that side. Right? Could have done that. Then what would we be in for? Resonance. Because you can't pick. They're both equivalent structures. If we have a double bond on this side instead, a single on that side, then you'd have to say, okay, they resonate between the two. But either way, they don't make the octet. How about SF6? Right? Fluorine is 7 times 6 is 42. Sulfur is 6, 48. 48 electrons. 1, 2, 3, 4, 5, 6. Fluorines. Okay, 2, 4, 6, 8, 10, 12. 36. So if we put 2, 4, 6 around each one of the fluorines, 6 times 6 is 36. We used them all up. So we have 2, 4, 6, 8, 10, 12 around sulfur, which is valid. Sulfur's in the third period, it has d orbitals available. But that's not an octet either. That's more than an octet. How about 4? O3. What is O3? Ozone. Ozone. So we have 3 times 6 is 18 electrons. So ozone would be like that as our skeleton. 14. Right? Start from the outside, work in. 2, 4, 6, 2, 4, 6. So that's minus 12 equals 2. So we put 2 more here. Okay. So it wouldn't do this oxygen any good to give up these 2 and make a double bond. Right? It wouldn't be any better off. Plus, it would exceed for that one. So we have to take maybe 2 from here, make a double bond. Or we could do it from the other side, in which case, resonance again. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. This one obeys the octet. How about, let's see, what's the last one? PCl5. Well, if you're in a hurry on a test, notice that you only give these 5 answers. So we found the octet. You can move on. But if we were to do PCl5, okay, phosphorus, 5, and 5 times 7 is 35, that's 40. 2, 4, 6, 8, 10. That means we have 30 electrons left. If we put 6 around each chlorine, 5 times 6 is 30. So we used them all up. And that's a trigonal bipyramid. But phosphorus has 2, 4, 6, 8, 10. It has more than an octet. So this one is the only one that obeys the octet rule out of that bunch. Okay? Did I go too fast? Okay. All right. That was 11. Let's see. I should have left those up there because 12 uses the same bunch. These molecules have a 0 net dipole moment. Let's see if we can remember which is which. All right, let's work from the bottom. PCl5 was a trigonal bipyramid with no lone pairs. So it has no dipole. It's all balanced. SF6. See, this one was PCl5. PCl5. This one was 6. Fluorines bonded to sulfur with no lone pairs. It's octahedral, no dipole. Okay. BH3. It was a trigonal planar, no dipole. Okay. How about 2? NO2. So NO2 is like this, like that, and we had 1 here, and we had there, and 2 over here, like that. Okay. So the problem here is that you've got 1, 2, 3 groups. Only that's a part of a group, so that's kind of weird. It would be trigonal planar, except that that's an odd electron, so it's bent. In which case, we do have a dipole. So you got a dipole with this one. How about 4? Oh, ozone. Okay. Ozone like that, like that, that, that. So around the central atom, you've got 1, 2, 3. Right? 3 groups, which means trigonal planar, cover up the lone pair, and you have a bent molecule. This one has a dipole. So the only one that has no dipole is 1, 3, and 5. 1, 3, and 5. Okay? Let's see. All right. 13. Let me scroll back. All right. So this skeleton, 2, 3, 4, this and here. Those subscripts, 1, 2, 3, and 4, those are not numbers. They're not there to say how many carbons there are. Those are just numbered carbons. Probably would have been better if we put like a 1 here and 2 there, like this. Then there would be no mistake. But the question is, how many electrons do you have to show, both bonding and non-bonding, in the Lewis structure? So you really don't have to do much with this except count electrons. Valence electrons. 1, 2, 3, 4, 5, 6. Hydrogen. Carbon has 4. 1, 2, 3, 4, 16. Oxygen has 6. So that's 28, right? Yeah, 28. There you go. Now the next one uses that same diagram, only this one says how many electrons are shared between carbon 2 and 3. So we want to know what's going on between these two. Right, we can't put any more electrons here. We've 28, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We got 8 more to go. Work from outside in. Those are all used up. Can't put any more on hydrogens. 1, 2, 3, 4, 5, 6. 2 left over. So where does the 2 go? The rule, or the suggestion is, just move to the next one and put them there. If we do that, if we put 2 here, then we've got an octet here, we've got an octet here, but these 2 are left out cold. There's no way to get an octet out of those guys. So you try to figure a way to get octet. In order to do that, the best way is to move those lone pairs over here. Now we can move them into that position and make a double bond. Okay, that way you've got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And everybody's happy. Okay? Okay, so to answer the question, how many electrons are shared between 2 and 3? 2, 4. 2 for each bond. So that's why C is the answer. All right, let's see. And I'm going to start skipping. How about 16? 16 showing. In the Lewis structure of ICl2 minus. Right, so we have an ion here. You can still draw Lewis dot structures for ions. You just have to be sure and take into account that charge. So we have 3 halogens with 7 electrons each. That's 21 plus 1 is 22 electrons. So I know the rule of thumb is the most electronegative is in the center. But in this case, we're going for symmetry. Symmetry puts iodine in the center and chlorine on the outside. Like that. So we've used up 4. 18 electrons. 2, 4, 6, 8, 10, 12. Okay. Minus 12, that means we got what, 6 more? 2, 4, 6. It just occurred to me, iodine also needs to be in here because it can more easily accommodate an excess of the octet, right? 2, 4, 6, 8, 10. Now, they both have access to d orbitals, but iodine has access to 5d, and chlorine only has 3ds. Okay, so this has got an octet, that's got an octet, and iodine has more than an octet. So that's as far as we can go. It doesn't help to make double bonds, anything like that. That's it. It doesn't ask us, no, it doesn't say what the structure is. It just says how many lone pairs. There's the key, lone pairs. How many pairs of electrons? Not how many electrons, how many pairs. There are 3 pairs around that iodine. So that's where your answers. And of course, if you read it wrong, you say, how many lone electrons are there? Well, there are 6, but 6 is not an answer. So that says, oh, wait a minute, let's reread that. Lone pairs. All right. So you don't have 7, no, skip 17, go to 19. There's 19. How many resonance structures can be drawn for a molecule O3? We did that one earlier, right? We could have that one or that one. And this would have 2 there, 2, 4, 6, 8, 2, 4, 2, 4, 6, 8. 2, 4, 6, 8. So we could put a bond on this side, or we could put a double bond on this side, which means there are only 2 resonance structures possible for ozone. 20. Oops. Scroll just a tiny bit. There we go. 20. Stop and think on this one. Which of the following types of molecules always has a dipole moment? Now, this flies in the face of what I may have said in the past. Right? You need to know 2 things to determine the dipole moment for a whole molecule. Right? Polar bonds and geometry. This adds a twist. Right? Rule number 0. Look for lone pairs. Also. Linear molecule with 2 identical bonds. That's definitely non-polar. The tetrahedral molecule with 4 identical bonds, equally spaced. There are no lone pairs in these guys. Linear molecule with 2 identical bonds, tetrahedral with 4 identical bonds. That's non-polar. C, trigonal pyramid molecule with 3 identical bonds. How do you get a trigonal pyramid molecule? We're not talking electronic, we're talking about the molecular structure. The only way to get a trigonal pyramid is to start with the tetrahedron. And you have something in the middle, and then you have an atom there, an atom there, an atom there, and a lone pair up there. Then, if you cover that up, you have this one at the top of its new pyramid, a trigonal pyramid there. And that lone pair, even if all these bonds are nonpolar, you still got that lone pair up there, giving you a negative preponderance in that part of the molecule. So that's why lone pairs have to be considered also. I didn't say this in lecture, just occurred to me. Now, if you have polar bonds, so much the better for the polarity. But this structure will always be polar because of that lone pair. Trigonal planar molecule with 3 identical bonds, that's always nonpolar. Like boron trihydride. None has a dipole moment. No, that one does. Example, ammonia. You just put a nitrogen here and hydrogens here. And you got your trigonal pyramid. Plus the bonds are polar in that case. That's why I wanted to do that. Let's see. I might have to skip 1 or 2. 22, we can knock this one out pretty quick. Which choice has bonds listed in order of increasing bond energy? This one focuses on, well, increasing bond energy. This one would be the strongest bond energy here for the same reason that dichlorine is, simply because of the distance between them. This one you start to get repulsive forces. So this one should be switched with HF. This one we've already talked about. That's in the wrong order. Dinitrogen is a triple bond, carbon-carbon bond, and C2H4 is a double bond. So dinitrogen is a stronger bond than this one. Triple bonds are stronger than double bonds. So that one's in the wrong order. But this one, where you have a single carbon-carbon, double carbon-carbon, triple carbon-carbon, as you add bonds, all else being equal, you add bonds, you get stronger bonds. And the atoms are closer together. It's not a linear increase. Right? This one's not twice as strong as that one, but it's a substantial increase. And so is this one. Okay. So that's 22. It's B. All right. Let's see. I'm going to skip 23. I had that one marked, but it's fairly straightforward. I'll come back. I got 25 and 26 marked. I'm going to come back to those if we have time, because I want to get to these other things. Okay, let's do 27. Oh, you got to scroll back. 27, we're going to make use of Hess's law again. So in this case, we've got these 3 reactions, and we need to combine them in such a way that we can answer this question. What's the bond energy of HF? So in order to use this information, you've got to know how to write the equation that's used to determine bond energy. Bond energy would be HF gas yields H gas plus F gas. Individual atoms from this molecule. How much energy goes into that? Okay? All right, so now now this is our target equation. That's the real trick to this one. After this, it's just Hess's law. So we've got HF on this side, HF is on that side, and there are two of them. So we need to flip it and take half of it. So that would be HF yields 1/2 H2 gas. And in these types of reactions, the phase is important. You need to keep the phase designators in here. And this energy is going to be half of 542, only it's positive. So that's 271, is it? Kilojoules? If I did that right. So we got this one taken care of. Now we need H. So this is on the correct side, but we only need half of it. So we need 1/2 H2 on this side yields H on this side. And the value then is still positive, but only half of that value. So what is that? 226? Is that right? No, 216. Correct? Yeah, 216. How about this one? A similar reason. We need half of that one. Like half of this one right here. Because we only need one of those fluorine atoms. So we take half of that equation. And now this is 70. My mind's going blank. 77. Correct? So, do we have everything we need? That one, this one, that one, that one. This one cancels that one. This one cancels that one. Good. So we can add these up now. So let's see. 13, 14, carry the 1. 8, 9, 16. 1 and 4 is 5. Plus 564. There it is. Okay? Let's see. You know, if we don't finish these today, you may have to go, and I definitely have to go. I did this same review, and I had more time on the Greenbrier campus yesterday. So I covered all of them that I have marked. So what I'm going to do is, this is for your benefit right now, and I'll post this one, plus I'll post the Greenbrier one from yesterday. So that anything that I missed in here, you can pick it up in that one. Let's see. I'll come back to that. 28. I'll come back to 28 if we can. I'll tell you what, I'm going to work backwards now. I'm going to go to the last page, to the short answers, and work backwards. Oops. Scroll down. There we go. So this is 53. In spite of the larger electronegativity differences between bonded atoms, beryllium dichloride and sulfur dichloride, so what are they saying? The electronegativity differences between these two is very small. The electronegativity difference between these is very large. Right? But the fact of the matter is, this one's nonpolar, and this one is polar. So what does that tell you? That tells you that geometry plays a major role in these molecules. Beryllium dichloride. So if we have beryllium's got 2 valence electrons, these 2 chlorines together have 14, so we got 16 total. Okay, there's 2, 4 is 12. All used up. Beryllium is linear, and these dipoles cancel each other. Whereas sulfur dichloride, let's see, sulfur would be 6 and 14 is 20. 20 electrons. So there's sulfur, there's chlorine, 2, 4, 16, 2, 4, 6, 8, 10, 12. So we have 4 left over. Okay, around sulfur we have 4 groups, which means a tetrahedron. So we have a tetrahedron here. Should draw it bigger. Now, where do they go? I like to put the atoms out here. And then in the back, sulfur's in the middle. And in the back, we have a lone pair there and a lone pair there. So the bond is between here and here, here and here, with about, well, starts off at 109.5 degrees, but it's really closer to 107 because of those lone pairs. But what is the molecular structure? Same as water. It's bent. So the dipole is probably this direction. But you still got those lone pairs to consider. So I'm not sure. The dipole is probably, these 2 are canceled out. The dipole goes toward the lone pairs. That's my guess. But to answer the question, the reason this one is polar is the geometry. So that's what this blurb says right here. This linear geometry cancels out. Bent geometry makes it polar. And then let's scroll back. Let's page. There we go. That's good. ICL4 or 54. Oh, that earlier one we had, what was it? ICL2. It had a charge on it. When I drew the structure, I forgot to put the charge on it. You need to put brackets and a charge. I'll be sure and get this one right. ICL4. Minus. Okay, so we have 5 times 7 is 35 plus 1 is 36 electrons. So iodine's going in the center. We have chlorides here. 2, 4, 6, 8 means 28 electrons. 2, 4, 6. 6. 6. So 6 times 4 is 24. That means we have four electrons left over. They have to go on the iodine. So the electronic structure is octahedral. And so there's a square in the middle. And then there's iodine in the middle here. And then for octahedrals, when you have lone pairs, balancing them is best, not on the square, but on the apexes. Now, when we have a trigonal bipyramid, for some reason, those lone pairs prefer to go on the triangle. But for this one, they go like that. And of course, we need our charge. So with all the other drawn in there. Actually, this is a perfectly good Lewis dot structure. Just put the charge there. You can draw it that way, it's perfectly fine. But this tells you whether it's polar or non-polar. all these bonds, they're going to be slightly polar because chlorine is more polar than iodine, but they all cancel one another out. And then these lone pairs cancel each other out too. So the entire molecule is nonpolar. And its structure is square plane. Okay. We got 10 minutes. No, yeah, 10 minutes. All right, so let me back up. How about 50? Oops, wrong direction. Wrong direction. Yeah, I need to scroll that. That's good. Okay. Use the bond energies given here. And these are all the ones you need to determine what's the enthalpy of this reaction. In order to use those bond energies, you have to know what bonds are present in each of those molecules. So when we write it like this, H3NH2, when we write it like that, that doesn't tell you what the bonds are. You need to know what the bonds are, or draw the Lewis dot structures. Right? This one we've done before. This one is like that, that, and that, with a lone pair over here. Okay? Hydrogen's easy. You got two of these, and you got one of these. So I'm not sure if I said in class, but when we draw organic molecules, if there are hydrogens that follow a carbon, those hydrogens belong to that carbon. They don't bond with the nitrogen. So we write it like this. Then the carbon is bound to the nitrogen. And you have another. That. And let's see, I think there's a lone pair here also. So those are your bonds. Now you can use the bond energies once you know what the bonds are. For this one, and you're gonna add up the energies for this side and subtract the energies for that side. All bond energies are written as positive values because of the way they're determined. You take the molecule or the bond and you throw energy at it until it breaks. So it's always input the energy. That's why these values are always positive. And the only way to find out what the reality is to say this side minus that side. Because you put energy in here to break bonds and you get energy back here, the negative side. Okay, so what we do is carbon, hydrogen, we've got one of them, 413. Okay, and we're going to add carbon, nitrogen, triple bond right here, 891. Then we're going to have two hydrogen-hydrogen bonds right here, 432. Okay, now we're going to subtract everything on this side. So we have 1, 2, 3 carbon-hydrogen bonds, which is right here, 413. And then we're going to add together that one, carbon-nitrogen bond, 305. Okay. And then 2 nitrogen-hydrogen bonds, right here, 391. Okay, that's the hard part. The rest is number crunching. So let's see, 413 plus 891, and 2 times 432 is 864. And then we're going to subtract whatever I add up here. So 3 times 413, 305. I want to subtract that. I get minus 158 kilojoules. Right here. And notice the creator of this question is sneaky. They put a positive 158 there. So if you get it flipped around, you're going to come up with a positive number and get the wrong answer. Okay, that was 50. Let's see. 5 minutes. Let's do 49. Choose the member of each set that best matches the label. So what we're saying is, which one's more metallic out of this pair? Which one more covalent out of this pair? Which one's highest electronegativity out of that pair? So 1, 2, 3, 1, 2, 3 is the way we match those up. Okay. So the more metallic, beryllium or barium. What do they mean by metallic? The more metallic is the one that wants to give up its electrons more readily. That means the one with the lowest electronegativity will be the more metallic. So beryllium should have a higher electronegativity than barium. So barium would be the more metallic. Okay, that's what they mean by that verbiage. The more covalent, N2O or MgO. The more covalent would be the one with non-metal, non-metal, not metal, non-metal. So the more covalent is this one. And the highest electronegativity out of these three, O, S, Br. So we just look at how they're arranged on the periodic table. There's oxygen, there's sulfur, there's bromine. The more electronegative should be oxygen. So it'll be barium, nitrous oxide, and oxygen. Barium, nitrous oxide, and oxygen. Thanks, back. Yeah, coming down. I have 51 and 52. Let me show you 52. We'll never run out of time. But the key to 52 is understanding what those abbreviations mean. 52. Here we go. See, what does this mean? You got these enthalpies for it, but what do they mean? This one is self-explanatory. You're sublimating the rubidium from solid to gas. You know, that's all there is to it. This one, IE1, is ionization energy, the first ionization energy for rubidium. So what would that mean? That would be rubidium, gas, yields, rubidium, ion, gas, plus an electron. Okay? That's what that would mean. Be, bond energy. So bond energy for this one is Cl2 gas yields 2 Cl gas. Okay. Delta HF. Enthalpy of formation. Remember how to do that one? Enthalpy of formation, rubidium chloride. You start on the right. Rubidium chloride. The most stable form, if this is solid, rubidium chloride, because it's an ionic compound. And then you work backwards. So you start with the elements. Rubidium is a metal, so it's solid. And then chlorine is diatomic gas. But you only need one of them. So that's what rubidium, this HF for rubidium chloride means. EA. Remember that one? Electron affinity. For Cl. Cl gas plus an electron yields Cl minus gas. That's what those values mean. So once you know this, plus the top one is self-explanatory, then you can calculate the lattice energy. All right, what do we mean by lattice energy? Lattice energy for rubidium chloride. Let's see if I'm right. Rubidium, yeah, 1+. The lattice energy for rubidium chloride is calculated as rubidium plus ion gas plus chloride ion gas yields rubidium chloride solid. So that's your target equation. And you use these plus the top one to find that. Okay. Now I go through this complete discussion in the green bracket, but I wanted to be sure and hash out these things right here because it could be a mystery. 51 is explained it's got all the equations there. So we don't have to explain that. And I'm over. Okay, so I guess that's all we have time for. And let's see. Now, while I was processing the video when we started class, so it should be finished now. So I can post it this evening. And that one, the Greenbrier will be available this evening. And this one should be available by tomorrow sometime.